For centuries, the planet Mercury has been shrouded in mystery. As the closest planet to the Sun, Mercury experiences extreme temperatures and has no atmosphere to protect it from constant bombardment by solar radiation. These conditions make it incredibly difficult to get clear images of the planet's surface. But that all changed in 2011 when NASA's MESSENGR spacecraft entered orbit around Mercury and began snapping high-resolution photos of the rocky world. After analyzing the trove of images beamed back by MESSENGR over several years, scientists have finally been able to peel back the layers of Mercury's secrets and reveal what lies beneath in unprecedented detail. Prior to MESSENGR, only brief flybys of Mercury by NASA's Mariner 10 spacecraft in the 1970s had captured close-up glimpses of the planet. Mariner 10 imaged about 45% of the surface, but at low resolution and with large gaps in coverage. The spacecraft also found evidence that Mercury had a weak magnetic field and very little atmosphere. For the next several decades, astronomers could only guess at what the remaining unexplored portions of Mercury might look like. The MESSENGR mission, short for Mercury Surface, Space Environment, Geochemistry, and Ranging, promised to change all that. After launching in 2004, the spacecraft completed flybys of Earth, Venus, and Mercury itself to fine-tune its trajectory before settling into orbit around Mercury in March 2011. This marked the first time a spacecraft had ever achieved orbit around the solar system's innermost planet. At last, MESSENGR had Mercury squarely in its sights and could begin surveying the entire planet in fine detail. Over the course of its 4-year primary mission in orbit around Mercury, MESSENGR photographed 100% of the surface at resolutions as high as 90 meters per pixel. It also measured the planet's composition, magnetic field, topography, and more using a suite of 7 scientific instruments. The orbiter even confirmed the presence of water ice and organic compounds at Mercury's North Pole, which lies in permanent shadow inside crater rims. Now that MESSENGR's trove of data has been fully returned to Earth, laboriously analyzed and published, the scientific community has reached an astonishing number of revelations about the planet closest to the Sun. By piecing together this new global portrait of Mercury bit by bit, our understanding has drastically deepened. One of the most important discoveries from MESSENGR was just how dynamic Mercury's surface geology turned out to be. Scientists had assumed Mercury's surface was relatively inactive and unchanged over billions of years, but up-close inspection by MESSENGR revealed a shocking number of surface features that could only have formed much more recently. Rather than the static planet that scientists expected, MESSENGR images showed that Mercury has been molded by a variety of geological processes over time. Some regions contain unmistakable signs of volcanic activity, such as lava flows, vents, and domes. Other areas exhibit evidence of deformation caused by global contraction as the planet's interior slowly cooled. This created lobate scarps, cliffs up to a mile high and hundreds of miles long, as one side of a fault line was thrust upward over the other. But one of the most striking geological features revealed by MESSENGR are known as hollows, the first direct evidence of current geological activity on Mercury. Hollows are regions where some material has been melted, vaporized, and lost to space, leaving behind irregular, shallow, rimless depressions in the crust. The formation process of hollows isn't entirely clear, but they are associated with bright deposits that may consist of pyroclastic ash erupted from small volcanic vents. The presence of hollows suggests Mercury's interior still contains enough heat to drive volcanic processes today. In addition to geological features, MESSENGR also spotted evidence of space weathering across Mercury's surface in the form of comet-like tails extending from impact craters. These crater rays form when an incoming meteoroid hits the surface and ejects bright dust across the surrounding terrain. Sunlight scatters off the ray material in a way that makes them visible. By tracking the changing brightness of crater rays over time, scientists were able to monitor the slow accumulation of microscopic meteoroid dust on Mercury's surface. Mercury's cratered landscape also harbored surprises. The planet's largest impact basin, the 1,500 km wide Caloris Basin, was found to be encircled by an unusual series of radial graben-like troughs emanating from a central region. This provided confirmation of the idea that seismic shaking following the Caloris impact triggered large-scale geological deformation far from the initial point of collision. Smaller impact craters imaged by MESNGER also exhibited floors partially covered by unusual platy material that may have formed by melting during the impact process. Investigating the composition of rocks on Mercury's surface was another avenue opened up by MESNGER's detailed photos. Subtle color differences in surface material allowed scientists to distinguish between chemical compositions and map the variation globally. For example, high magnesium regions correlate to ancient lava plains, while low reflectance material tends to contain more iron and calcium. By matching up these composition patterns with surface features, MESNGER revealed crucial clues to Mercury's geological history. One of the first surprises from the Mariner 10 flybys in the 1970s was the discovery that Mercury possesses an active magnetic field, making it unique among the solar system's inner planets. But the rapid flybys obtained only a crude glimpse into the properties of this field. By spending a year in orbit closely studying Mercury's magnetism, MESNGER was able to unravel the origins and dynamics of the planet's magnetic field in far greater detail. MESNGER measurements confirmed that Mercury's magnetic field is approximately dipolar, much like Earth's, meaning it resembles the field that would be generated by a simple bar magnet at the center of the planet. But its strength is just 1% that of Earth's magnetic field. Interestingly, analysis of magnetic field data shows that the field is offset northward by about 20% of the planetary radius relative to Mercury's geographic equator. The tilt of the magnetic axis also produces an asymmetry where the magnetic field strength in the northern hemisphere is nearly double the strength in the southern hemisphere. Remarkably, MESNGER detected clear evidence of external magnetic reconnection occurring between the solar wind and Mercury's field, especially when the IMF was oriented southward. Reconnection redistributes energy and mass inside a magnetosphere and is the driving force behind space weather phenomena. Similar magnetic reconnection activity occurs between the solar wind and Earth's magnetic field. One long-standing puzzle was the staggering strength of Mercury's magnetic field compared to what models had predicted. But MESNGER measurements finally resolved this mystery by gathering the first precise measurements of Mercury's core size. It turns out the liquid outer core is much larger than expected, extending to nearly 85% of the planetary radius. This substantial size is more than adequate to generate Mercury's observed global magnetic field through an internal dynamo process like Earth's. But perhaps the biggest surprise about Mercury's magnetic field involved the discovery by MESNGER of miniature temporary magnetic fields concentrated around certain regions of the planet's surface. These magnetic anomalies are suspected to arise from magnetization of crustal material by past lunar dynamo activity early in Mercury's history when the core cooled and solidified. The persistently strong remnant magnetism frozen into these surface rocks provides vital clues to the planet's early magnetic history. Prior to MESNGER, little was definitively known about the tinous envelope of gas and dust surrounding Mercury known as its exosphere. But spectroscopy measurements by MESNGER provided the first conclusive identification of the composition, distribution, and dynamics of the Mercury's exosphere. One surprising finding was that Mercury's exosphere is composed predominantly of calcium, magnesium, and sodium atoms rather than volatile compounds like water vapor or carbon dioxide. The calcium and magnesium originate from surface rocks vaporized by micrometeoroid impacts. Solar radiation pressure and photon momentum then launch these atoms into ballistic trajectories, forming the exosphere. MESNGER also confirmed that Mercury's sodium exosphere exhibits a comet-like tail that extends anti-sunward for tens of thousands of miles and seems to be periodically enhanced. The source of the sodium remains uncertain, but may be linked to the photon-stimulated desorption of sodium atoms from surface regolith grains. But some of the most perplexing MESSENGER discoveries concern the polar regions of Mercury. Earth-based radar images had revealed highly reflective regions near the North Pole, possibly indicative of water ice deposits inside permanently shadowed crater regions. MESSENGER's neutron spectrometer identified a large enhancement of hydrogen in the planet's north polar region, which was later definitively linked with surface water ice. The eroded walls of North Polar impact craters are believed to shelter these water ice deposits from vaporizing under the hot Mercurian sun. More recent visible and near-infrared imaging has revealed that some North Polar deposits are also rich in organic compounds called tholins. On other icy worlds, tholins are produced when ultraviolet light interacts with a mix of water, methane, and nitrogen. This points to Mercury's poles as an intriguing natural laboratory for studying volatile transport and chemical processes on airless, low-gravity planetary bodies. The insights gained during MESSENGER's 4 years orbiting Mercury transformed our understanding of the solar system's innermost planet. Prior to MESSENGER's extended visit, Mercury was assumed to be a geologically inert world with few surprises. But up-close observations paint a picture of a dynamic planet with active volcanism, recent surface flows, and signs of ongoing cratering. Measurements of the planet's magnetic field and exosphere revealed equally unexpected complexity. Much work still remains to interpret the wealth of data returned by MESSENGER before the mission concluded in 2015. But it's clear our knowledge of Mercury has progressed by leaps and bounds thanks to the first orbiter to survey this extreme terrestrial world. The MESSENGER mission serves as a demonstration of how a single robotic spacecraft can profoundly alter our perspectives on one of Earth's neighboring planets when given the opportunity for extended study from orbit. Don't forget to like and subscribe to our channel so you don't miss new videos.